Andrew Cheng is a planetary scientist at Johns Hopkins Applied Physics Laboratory and lead investigator for the Double Asteroid Redirection Test mission, DART. He received his AB in physics from Princeton University in 1971 and his PhD in physics from Columbia University in 1977. He was previously deputy chief scientist at NASA headquarters. He was project scientist for the Near-Earth Asteroid Rendezvous mission, the first to orbit and land on an asteroid. And he was principal investigator of the LORRI camera on the New Horizons mission that went past Pluto and other objects in the far reaches of the solar system. Mr. Cheng, Dr. Cheng.
All right, thank you. I'm going to try to share the screen again. It worked before. Let's see if...
Okay, well, you're on full screen now.
And
okay, it looks like it's working.
There we go, working. All right, so I'll tell you about the DART mission. It was NASA's first planetary defense test mission. Planetary defense is about protecting the Earth from asteroid impacts. If we ever find an asteroid that's headed for Earth, what can we do? Well, we can try to prevent the impact with Earth by changing the orbit of the asteroid. And we would change it by running a spacecraft into it, just blocking it with the spacecraft, change the orbit so it missed the Earth. That's the idea. And the DART mission was the first test of that approach. We call it a kinetic impactor approach. To hit the spacecraft hits the asteroid, as seen in the, hits the asteroid, change the orbit. The orbit we change is the orbit of the, okay, we targeted a binary asteroid. That's why it's a dual or double asteroid mission. We targeted the moon of a binary asteroid, and we wanted to change the orbit of the moon around its primary. And we carried actually another spacecraft with us. It's LichCube. It's a briefcase size. It's a CubeSat, a 6U CubeSat. It was contributed by the Italian Space Agency, it's OSI, to the DART mission. And we released them 15 days before the impact of DART onto the target Dimorphos, and LichCube did its own flyby of the Didymos system and took some great pictures of what happened after the DART impact. All right. And why do we do this? Okay, we did this because we chose Didymos because at the time of our impact, late September, early October, Didymos is very close to Earth. And that makes it very relatively favorable to observe the outcomes of the impact from the ground. I'll get into why we wanted to do that shortly. So Earth-based observations, a big part of the DART mission. So what did DART do? There's four things. First, we wanted to hit Dimorphos to change its orbit. And there's a specific target at the specific apparition when it's close to Earth. We're changing the binary orbit period. It has to be a large enough change that you could easily see the change from the ground. We'll get into how shortly. We want to measure the period change. We want to see how much deflection. The whole idea is to deflect an asteroid's orbit enough to make it hit the Earth. So we want to do a test. We want to see how much of an orbit deflection we would get. And then the last thing is you want to measure momentum transfer, of course, because that's really how we quantify how much of a push we're able to get to change the orbit of an asteroid. What was the amount of momentum we transferred? The spacecraft brings a certain amount of momentum to the party. Then after the impact, how much did the target asteroid change its momentum?
Okay, you said you wanted to change it so it would hit the Earth?
So it will not hit the Earth.
We're not. Okay, good. That makes sense. I feel safer.
Yes, that's the idea. Now, in fact, Didymos is an object that was not going to hit the Earth anyway.
Yeah.
And we did not change its orbit sufficient. In fact, we changed it by an unmeasurably small amount, the Didymos, the whole system, that is. What we changed was the orbit of the moon around the primary, and that created a big change. We easily measured quite accurately, actually. Okay. And so I'll talk about the momentum enhancement. So the amount of momentum you transferred, it turned out, is a lot bigger than the amount of momentum carried in by the spacecraft. And the reason for that is because you created a lot of ejecta. And by throwing off ejecta, you feel a recoil force. So that force is very significant. All right, let's go. All right, so now we're showing here, okay, we have Earth. DART launches at some point. And so you can trace the orbit. There we go. DART is launched. It's in the yellow orbit. DART never gets very far from Earth. It's a low energy orbit. But what happens is we arrange things so that DART eventually puts itself in front of the asteroid Didymos, and Didymos system basically runs into it. So that's what happens. Kinetic impact was last September, September 26. Okay, so here was the impact. Okay, a quick picture of the spacecraft. I won't talk about that to us very much. We carried only the one instrument, the camera. It's an 8-inch camera, 8-inch aperture telescope. We needed that because we wanted to detect the asteroid more than a month before impact. And the asteroid's a small asteroid. It's less than 1 kilometer in size, so it's not that bright. We need a big telescope to be able to do that. And the other thing is that we wanted to take high resolution images and get them down to Earth. That's the most important point. The spacecraft was going to crash into the asteroid, so we cannot just store the images on the spacecraft and trickle them back, over the succeeding months after the encounter. We have to get everything back downloaded to Earth before the impact. That means that we want to take pictures at very high resolution because we want to know more about the surface of our target. We want to know where we hit, and we want to know about the geology of where we hit. And we have to get all those images back. That requires a long focal length, a large camera. So that's why we have this camera. I'll talk about a little bit more about that. Okay, this is what the view of the spacecraft you see here. This is the camera looking out at you. That's what, basically, if you were standing on the asteroid looking up and darts coming in at you, this is what you would see, the camera looking at you. Okay, so the situation is that the spacecraft guided itself. It was a guided missile, basically, homing in on the target. So the SmartNav autonomous navigation was actually, the terminal phase started 8 hours before the impact, and 4 hours before the impact, the spacecraft was put under the autonomous control. So it basically said, okay, you got the keys now after 4 hours. The autonomous navigation was firing thrusters and steering the spacecraft. The interesting thing, though, is that you can see what Dimorphos and Didymos looked like in this. This is a camera with arc-second. It's an 8-inch telescope at arc-second image resolution. This is what it looked like 1 hour before. You could it's barely resolved. The target Didymos and Dimorphos are so small, the target is barely resolved at 1 hour out. And not only that, before that, 2 hours out, you cannot see the target at all, Dimorphos. And the reason is that it's in the phase of its orbit where the moon is behind the primary Didymos as seen by the spacecraft. So you cannot see the moon at all because it's on the other side of the primary asteroid. So 1.5 hours before impact is when the target we want to hit actually emerges from behind the limb of the main asteroid. And so during that time, the camera has to recognize, okay, or the spacecraft, I guess, it needs to recognize that there's this new target, a new blob has appeared in the images. And then it has to recognize, okay, that blob is the one that we're supposed to hit, and it has to start targeting that. So 2.5 minutes out, you can see what the image looked like. The target now is well resolved. Also at 2.5 minutes out, basically the smart nav, the autonomous navigation system, stops doing orbit correction maneuvers. It's just gliding into the, coasting into the target after that point. And the reason is we want to get images. And so this is this is the last complete image that was shown here. And that's what the target looked like. 2 seconds out. So 2 seconds out, it's still 12 kilometers away. It's because we're moving at more than 6 kilometers per second. And so that's what the space, okay. And this is a movie. Let's see if we can play it. Yes, we'll play it. All right, so the autonomous navigation system is tracking. This shows already that we have already identified the moon. That's where the green circle was. Didymos is a perfect purple circle. It's 4 times larger. It's you know, more, it's close to 100 times brighter. But the spacecraft is zooming in. It's heading toward Dimorphos. At this point, we could see, oh, wow, you can see where we hit also. These are the final 6 images. You can see we hit between those 2 big rocks. There's a final partial image here. It's 16 meters across. So, and only partial image because the spacecraft met its end and never able to complete transmitting that image. Anyway, so we're all cheering at this point. We said, oh, wow, we hit. Fantastic. Okay. And we go on. All right, this is the same set of images. We can just watch it one more time, I guess. It's fun. So 4 minutes out, this is what it looks like. You start, Earth is 7 million miles away, and this is speeded up 10 times. The images actually come in one by one, about once every second or so. So Didymos is already moving out of the field of view. We're zooming closer and closer to the target. And there's our target, Dimorphos. Bam. These are the final images. It's filling the field of view. And okay, this is the last one. All right. So 2.5 minutes before, so the 2 objects are to scale here. We call this is the last, the highest resolution, complete, full disk image of Dimorphos. It's 11 seconds before impact. We call this one the fish. I have to do this to you. I'm sorry. I know you cannot unsee a fish once I say that. That's true for me, but I have to do that to you all. And this is right in the center of these 3 boulders. I don't know if you can see my cursor. That's where we hit. So very close to the center of the image. You see there's huge boulders here. The boulders where we hit are 6.5 meters. So they're larger than the spacecraft. But as you may recall, the spacecraft has large solar panels. So the solar panels actually extended beyond the size of these 2 boulders. So they basically lined up right along these 2 big boulders. They were hit by the solar panels. The spacecraft body hit actually between them. We think most likely both of these 2 boulders are completely destroyed. They don't exist anymore. So there we are. Well, I've already talked about these 2 boulders. This is the last complete image. All right, let me talk about it. Yes.
You weren't part of the ejecta?
The what?
You weren't part of the ejecta? The boulders weren't?
They were. I was going to, there's actually some indications we've seen individual big boulders in the ejecta. I wasn't going to show any of that. I don't think I'm showing any of that, but yeah, there are people on the team who are working on that. They see individual boulders and they're tracking them and they want to locate them, try to estimate how big they are, how fast they're moving and all that stuff. So yes, we do see individual boulders. Where they came from, we don't know yet. Dave, I'm going to say a little bit about the AIDA, which is the DART mission plus a European mission, ESA's Hera mission, which will go to the same target in 2026. And then also as part of that, we have here in the DART mission, LithiaCube. So I'm going to show a bunch of LithiaCube data now.
What's the Rubik's Cube?
What's the Rubik's Cube here? That is what the Hera spacecraft looks like. It's a box. Well, the DART spacecraft, I guess you cannot see very well. It's also a box. The body of the spacecraft is a box, and then it has these big solar panels. We have big solar panels because we had carried actually an ion engine we were going to use. We ended up not using it because DART was also supposed to do a flight test of this the new NASA ion engine. It's called the Next engine. We ended up not doing that test because it turns out the Next engine has some it put large current spikes the way it was. For some reason, it put large current spikes into the spacecraft ground, spacecraft bus, and we were not able to do that test. So anyway, that's why DART has such huge solar panels. LithiaCube, it's a suitcase, small suitcase-sized spacecraft. It has 2 cameras on it, and it flew by Didymos 3 minutes after the DART kinetic impact, actually 168 seconds. At 58 kilometers, it was 55 was a nominal design, actually more like 58. Okay. Interesting thing already is that while quite far away already showed the immediate, okay, where my cursor is and where you see a little ring alternating with a bright dot, it showed a dramatic brightening of Dimorphos right at the moment of DART impact. Now, the camera that took this, it turns out, has a problem. It's badly out of focus, and there's still, the Italian team is still working on how to correct for that. But that's why these images look so strange. But the result is, interesting thing is that there was an immediate brightness increase after DART hit by a tremendous factor. In fact, all right. All right, 3 minutes after the DART impact, here is Didymos. It's totally saturated in this image. And here's the plume. The plume and Dimorphos also is saturated. Despite appearances, the ejecta is not actually wrapping around Didymos. They're, it's just in the image they're projected. They look like they're touching, but in fact, they're not. This is really more what it looks like. So this is shortly before the closest approach. Where my cursor is where Dimorphos is. All of this out here is plume, ejecta plume, and here's the primary Didymos. And you can notice here that there's this huge boulder, right? This is close to the south pole of Didymos. You can see its shadow here. You can see also Dimorphos. There's a sunlit Dimorphos. And then the plume in front of it. And the plume, it looks optically, it looks like it's very thick. And possibly even casting shadows on parts of itself. It's that thick. All right.
Where did the increased brightness come from?
Increased brightness, it's just the sun shining. It's just the illumination geometry that it's closer to.
I thought the impact caused increased brightness.
Oh, no. Yeah, the impact did. The cause of that brightness was the creation of all the ejecta. So the ejecta is also very bright, and the total surface area in the ejecta actually is bigger than the surface area of the moon itself, of Dimorphos itself. That's why the total brightness went up, because we released so much material. It's reflecting sunlight, and so in the earlier image. Yeah, in the earlier image here, all you see is the increase in total brightness. It's because he released a lot more area, a lot more reflecting material, the ejecta. And this is what the ejecta look like. It's forming streamers. It's very complicated shapes. Here it is before. This is the same after closest approach. And you actually see its dark band or Dimorphos. The dark band is a shadow. It looks like the plume is thick enough at altitude that it's casting shadows both on Dimorphos and on itself. So that's very strange. Excuse me. There's color images from LithiaCube. These are the 3-color RGB false color images. they're not attempting to reproduce what the color would look like to the human eye. To the human eye, these will be brownish reddish objects. But in the false color, 3-color, it's showing up as different shades of blue and green. So again, it's the same 2 images, the Dimorphos after closest approach and before closest approach. What happened was right at closest approach, of course, the camera lost track of Didymos. We were hoping that it would be able to track Didymos right through closest approach. But again, at closest approach, the angular rate of the target is reaches a maximum. And the camera the lithic cube actually lost track of the target, and the target was out of the field of view. That's why there's no pictures between the 76 kilometers before closest approach and then 71 kilometers after. In between, we lost the target. All right, here's another. I think I could, yes. This is actually a movie showing all the lithic cube images. It's really fascinating to me. Okay, there, we just went through closest approach. You see the shadow, shadow, shadow. Weirdness. Okay. This is another image. I won't talk to that one. Okay, this is examples of features in the plume that the lithic cube team is tracking, including individual boulders, those 2 little circles. They have been able to identify them in successive images taken from their sequence. They actually returned more than 400 images. I'm only showing a few of them. They're looking at the colors of the plume and comparing them to the colors of Didymos. So they're finding variations. That work is still ongoing. And so the question is, what they hope to learn from that is whether there are small compositional differences between the materials in different parts of the plume, or between the plume and the surface of Dimorphos itself, or whether there are particle size differences. And that's still being worked. Anyway, interesting question, interesting work. Okay, this is actually a view of lithic cube being put into its dispenser, so you can see how big it is. It's like I said, it's sort of a small suitcase. All right, talk a little bit about the telescopic observations. There are a lot of telescopes all around the world on the ground viewing. These are both optical telescopes and also the big radio telescopes, and as well telescopes in space. So the Hubble Space Telescope, the James Webb Space Telescope, and the Lucy mission, they all observed Didymos for the DART impact. They all looked at the DART impact. Okay, here we go. These are some examples of the early observations. So you can see within minutes of the impact, there was, 5 minutes after the impact, you had a plume of material that was seen to emerge from Didymos and move away at high speed. Okay, so we're still working on that, what that means. But anyway, so it's literally, we were watching the NASA feed, we watched the final images come down from DART, and then literally within minutes, the ground-based observers were reporting to us, over the internet that, oh, we're seeing this plume, we're seeing the brightness peak, we see material expanding. Okay, so literally within minutes, so 10 minutes, 15 minutes after the impact, it's already going crazy. All right, and okay, this is another movie. Here it is, the moving dot is Didymos. Okay, there it is, and there goes the plume. All right, wonderful. So this is a material that's moving at many kilometers per second. It's not, we believe it's not the irregular solid particles being ejected from the impact, the DART impact. It's something else. And we think, some of us, we're working on what it might be, but it could be a vapor plume. So this is a cometary phenomenon. You release a bunch of gas at high pressure and it expands and it condenses, and then you see that. That would be able to account for the very high ejection speed. Okay, this is what it looked like from Hubble Space Telescope. Hubble only started looking hours afterwards, so it didn't see this early stuff. So Hubble on the left and the James Webb Space Telescope on the right, they're both oriented so the sun is in the same direction. So you can see the direction of the sun and also the direction that dart came from. In both of these images, I should warn you, you also see the diffraction spikes from the telescope. So there's 4 of those for Hubble, and there's 6 of those on the James Webb. So there are also diffraction spikes, you see. Here, Hubble pictures, 22 minutes. So the very first one, this is 22 minutes after the impact, hours after the impact. All right. I think this is also a movie. Yeah, no, it's not. Sorry, that's not a movie. But okay, this I included because it created a very long tail, Didymos here, the tail extending many tens of thousands of kilometers away. This image, I think, is over 20,000 kilometers going out past the edge of the frame. It's already 64 days after the impact. In fact, to this time now, if you look at currently, you look at Didymos in the sky, you still see this enormous tail that dart impact created. It's still there. All right. Okay. Why did we want to look at Didymos with telescopes, other than just it's great, it's cool, is we wanted to measure a light curve. That's what this blue curve is in the bottom. What happens when you look at the binary system that's oriented properly with respect to Earth and the sun so that it's eclipsing, is that the object sometimes goes behind, the moon goes behind the primary, it comes out, it can move in front of the primary, it can also cast shadows on the primary. And all of those change the brightness of the system. Those are called mutual events, and we time those. And if you time those, you can measure the orbit period of the moon. So that's why we do this. All right. And the point is that the orbit period changed, and if you change the orbit period, that's what this, if you look at it very carefully, you see a blue line and an orange line. The blue line is before the test, before the dart impact. The orange line is after the dart impact. Period changes, what happens is it changes the time at which you see these mutual events. And time is something we can measure very accurately. Okay, so again, the whole idea is the dark arrows in the top indicates when we should see the mutual events if the period did not change, and then the orange shows what happens because the period did change. And so here it is, the data. This is what light curve measurements look like. The expected time for the previous orbit period of 11 hours, 55 minutes. This is when the event was actually seen, consistent with a shorter period, half hour shorter, 11-hour, 23-minute orbit, which is what it is now. That's one event from September 29, another event from October 4. So that's what happens. That's what we did. Okay, radar observations as well, using the big ground-based telescopes. This is the Goldstone 64-meter. These are examples of what's called delay Doppler images. So this is the axis here is in strange units, but it's distance from the Earth. When going across the image, it's actually a measurement of the velocity, radial velocity relative to Earth. So positive and negative. Negative one side, positive the other. So this bunch of lines here is where Didymos is, the moon. And the moon is, this picture is here. The moon actually follows an orbit. That's how you can trace it around. So the moon is up here where I have my cursor, and the moon is down here where I have my cursor. Oh, okay, it's already told you. There's Didymos. There's one moon, it's a little bit in green, and there's the other moon, and it follows an orbit. You could trace an orbit. Okay. So we trace it. Anyway, so the radar was actually also able to measure the period change, and it actually got us our first measurement of the period change within days after the impact. Okay. All right, so what's the whole story here? We wanted to determine the momentum enhancement. Why is that? Because the if you want to change, cause a deflection of a body that's moving, change its velocity by something, you have to change its momentum. You have to add a certain amount of momentum. And so we know in the case of the DART impact, the spacecraft brought a known amount of momentum into the impact. And if it hits the body, it just just sinks into the body. They stick together after the impact. Then there's no momentum enhancement because that's the amount of momentum you transfer. What the spacecraft brought in is just transferred to the target, and we say that momentum enhancement factor is 1 in that case. There's no ejecta. But if
your momentum transfer, that's in relation to what the
spacecraft incident momentum.
Okay, but that's in relation to what? I mean, if I'm on the spacecraft, I don't have any difference in momentum with the spacecraft.
Okay, well, yeah, you can look at it. You can look at it if you want in the center of mass frame, or you can look at it as on, either way.
Okay, but this is
yeah, whatever frame
the change in
have,
momentum of the moon in respect to its I don't know what to say. The asteroid it's orbiting.
Yes, the moon. Okay, the moon has a certain orbital velocity. The moon has a mass. It has a certain amount of momentum, linear momentum, at the time of the impact. The change in that linear momentum, what is the change in that linear momentum compared to the momentum of the spacecraft? And you can choose whatever reference frame you want to look at that.
Yeah. Okay, yeah. I mean, my question is, what reference are we using?
Most of the time, we just use the inertial frame, which is in which both the spacecraft and the moon are moving. That's what people usually use. But you could use, center of mass between the two. But you calculate. All right. The point is simply that because you created ejecta, you threw material off, the ejecta carried off some of the momentum that you brought in. And so you have to, it increases the amount of momentum that goes into the target. And the result we found was that, in fact, you created so much ejecta that the amount of momentum transferred to the target is almost 4 times greater than what the spacecraft brought in. So that was an interesting result. How do we do that? We started from the orbit period change. So that change implies a change in velocity. So the orbit period, we have independent measurements of basically from the radar data, using also from optical data. You know how large the system is. And so the orbit period change determines a velocity, a speed change, the orbit speed change. It was 2.7 millimeters per second. That's what DART did. We changed the velocity of that guy by 2.7 millimeters per second. But then we had to do full two-body, meaning that did not actually use Kepler's laws, or even even Kepler's laws augmented by oblateness corrections and things like that. But full two-body dynamical simulations accounting for the shapes and sizes of both bodies. Reason being that they're quite large compared to how far apart those two bodies are, Didymos and Dimorphos. One is 780 meters in diameter, the other is 160 meters in diameter, but they're only 1,180 meters apart. So they're quite close compared to their sizes. And the result is they don't behave like point masses at all. They don't, and the deviations from the Keplerian motion are very significant. We have to take that all into account. Anyway, so that's what we had to do. Use the full two-body dynamical simulations to determine the orbit speed change. And then also looking at the images and knowing, we know the sizes of both bodies. We know the total mass of the system. That's what the Kepler laws are. That's what this dynamical analysis tells you. You know the total mass of the system, but we don't know how the mass is apportioned between the two bodies. And that boils down to not knowing whether Dimorphos, the moon, is the same density as Didymos or higher or lower. And that's what is reflected in the chart. So we assume that if the two bodies, the moon and the primary, have the same density, that's about a density of 2,400. It's the middle of the chart. And for that value, the beta, the momentum enhancement, was a factor of 6. If the moon is more dense and it's actually heavier, then to get that same speed change, you had to have a bigger momentum transfer. So that's what this curve is showing. And so somewhere between at least 2 and maybe as much as 5 times the momentum of the spacecraft was what we put into the moon by the DART impact. Looking at other objects for which we've actually measured the density. So Eros, for example, density of 2.7, so 2,700 in these units. I'm sorry, I'm old enough that I like to use CGS units still. But 2,700 Eros, the other asteroid, S-type asteroid, it's up here. There's another S-type asteroid, Itokawa, that was visited by the Japanese Hayabusa mission. It's down here, density is 1.9. So it's down here. There's another radar measure asteroid called Mashup. It's another radar binary. Its density is also known, and it's down, it's a little bit under 2 also. And okay, so that actually is my whole story. There's more pictures we can look at. This is, you know, the DART spacecraft as it is about to go into thermal vacuum testing. You can get an idea of how big the solar panels are by looking at this is testing at the manufacturer of the rollout solar arrays. And the rollout solar arrays cannot actually be rolled out without special equipment to support the thing, because in Earth's gravity, the solar panel could not support its own weight. It has to be accurately, you know, carefully suspended to be able to prevent it from collapsing under its own gravity. And this is what the Draco camera looks like. Looking, this is you're under the spacecraft, looking up at the camera. There we are, going out to the spacecraft and launch. Okay, that's all I had to say.
Andy, I have a question.
Yes.
I'm just wondering, is there any information on how deep the impact went into the target? In other words, did the spacecraft disintegrate right on the surface, or did it penetrate deep into the
yeah, the space, okay. Good question. There's numerical simulations would shed some light into that. And based on what I think we would have seen from that, by and large, yes, the spacecraft would disintegrate right at the surface. There may be parts of it. I don't think that there have been simulations, but you know, there are solid metal pieces in there. They might penetrate to some depth. So I think it's a good question. I don't actually know the answer, but by and large, yes, the spacecraft disintegrates at the surface. Most of it will disintegrate. Spacecraft carried a lot of actually fuel into the impact as well, and which is why I mentioned the possibility of a vapor plume. It carries close to 90 kilograms of fuel into the impact. It was mostly xenon and some hydrazine as well. So that would have been, so all that is released right at, you know, right at pretty much the fuel tanks break up, and that's released right at the surface.
Do you think that vapor cloud you saw was due to the fuel?
It could be. There's also some vaporization of the target, but again, that's work that people are looking into the question. My own opinion is it's probably mostly fuel, yeah. But 90 kilograms is a lot of fuel.
Yeah, yeah.
I'm going to ask a question here. I have a question.
Yeah.
Regarding the orbit that was chosen to do the impact.
Mm-hmm.
Had you circled around the your DART project the other way, so it collided head on with the Dimorphos and Didymos, how much difference would that have been in terms of momentum impact?
Okay. It's a rather small difference, although actually it turns out it's okay. Well, we had let me go back. We had the choice. Go back to the very beginning, very beginning. Okay, this is the best chart to look at. Okay, we're not actually. Okay, DART comes in from this side. I'm not sure what you mean. We could have the heliocentric orbit to put DART on to make it come in from the other side is probably not feasible for us, because that requires a lot more energy. There's a much bigger launch vehicle required to do that. What choice we actually had was to hit here, or to change the time of the impact by 6 hours and hit on the other side. That's the choice we actually had. So in other words, here, the way that you can see these little arrows, this was what we actually did. It was a close to head-on impact. If we had chosen the impact time 6 hours different, then you would have hit it from the rear, if you like, so boosting it. So that's a choice we could have chosen either one. We chose to do it this way because it turns out that the sun is in the direction. We wanted to do it in the sunlit side rather than the night side. So it was a matter of choosing the lighting that we wanted to have for the target.
Yeah,
you needed the lighting to take the pictures too.
Yes. Well, yeah. So
you answered my question in that the direction of the DART coming into the system,
right.
If you had done it from the other direction, you would have required a whole different launch system to get there. Yes. And that's the reason. Yes. But so I mean, I'm the other question is, did Dimorphos, being a smaller body, probably because of gravity, much less dense than Didymos.
Maybe, we don't know.
Okay, I was just wondering if you'd expect as much ejecta if you hit Didymos as you got from Dimorphos.
That's a very good question. I suspect if you took a poll, asked different members of our team, you would get as many different answers as you asked, as people you asked. So that's a good question. I don't know. But there's even the question of whether Dimorphos would have higher or lower density than Didymos. And you've got people on our team lined up on both sides. It should be higher or it should be lower.
Well, I guess the fact that there's so much disagreement within the team, yes, indicates that we definitely need to visit more near-Earth orbit objects to understand them better.
Yes, I think that's a fair conclusion. Yes. So we don't know. We don't know.
Well, thank you very much for a very interesting presentation. I've enjoyed it immensely, and thank you for sharing your adventure here with us, and we've enjoyed going along with you.
Okay, thank you. I'm going to stop share in that case, and all right. Oh, yeah, we have something in the chat. Let me just have a quick look at that. What is illuminate object on the dark? Oh, that's a very, I'm not sure. Okay, let me go. What is the illuminated object on the dark side of Didymos at about 8 o'clock in pre-impact image?
I think that's the tail of the fish.
Yes. Ah, yes, the tail of the fish. Yes, that's a big boulder. It's on the dark side, but it's big enough to stick up into the sunlight.
Wow.
Yes, it's a huge boulder. It's actually a huge boulder, more than, it's 20, 30 meter kind of. So bigger than the spacecraft, the DART spacecraft, by a lot.
By the way, these boulders that you mentioned, are they likely to be fairly dense, or ice or something like that, or what?
Not ice, but rock, actually, yeah. Like
rock?
Meteorites, we think, sure.
Okay.
Yeah, so close to solid rocks. We think that's what they are. Again, wow. That's something we can't actually know for sure, but that's what I think most of us would assume to begin with. It looks like a rock. It probably is a rock.
Yeah, a lot of these asteroids seem to be rubble piles.
Yes, they do. This one does also, yes.
Yeah.
It'll be interesting once Hera arrives to see which of the boulders on the pre-impact DART images are still there.
Yeah, that's very interesting. Yes, very interesting question. Or even if the rotation state is anything like what it is now. Yeah, lots of interesting questions. And how big is the DART crater? It was asked. That was one of the questions I guess I never answered. How deep is the crater? How big is it? Well, there's a wide diversity of opinions on the team even about that. We don't have a simple answer. That's something else I think that Terrible will finally settle when we get there. Is there a crater, and how big is it? And how deep did we go?
For the next mission in 26 that's going to visit there.
That is Hera, by the way.
Will that be a flyby, or will you actually slow down and go into orbit with them?
Yeah, it's a rendezvous mission, so it will slow down. It doesn't actually orbit the body. It will release 2 CubeSats. The CubeSats will orbit the body, but the main spacecraft itself will not. It's this body is so small that it's actually hard to orbit the guy. It's better just to stand off, 10 or 20 kilometers away.
And maybe the CubeSats might be able to get separate mass measurements of Dimorphos.
Oh yeah, that's the
Didymos.
idea. That's the idea.
Hmm.
Yeah, and also the main spacecraft will be able to get a mass measurement by looking at measuring reflex motion of the system. So using the camera. Anyway, yeah, lots of excitement we would expect also from Hera mission. Really looking forward to that.
That's in 26, right?
They arrive in 26, yes, and their science phase starts in early 2027.
Oh, okay.
Yep, I hope I'm still going to be around to look for that.
That'll be very interesting.
Mm-hmm.
If there are no more questions, there are no more comments, I guess that essentially concludes our meeting and talk. And again, our thanks to you for interesting talk.
Yeah, thank you. It's been a pleasure.
Yeah, maybe in 2026 we'll have you talk again.
Okay.
Or 2027 when.
Yeah.
Yes, I actually might have something to say.
Well, I think you'll always have something to say.
Sure. Yeah, good things or not good things, yes.
Well, thank you very much.
Okay, thank you.